Well, hello there, ladies and gentlemen. So today we're going to continue on and look at another cycle. So we've looked at for the air standard cycle analysis, we looked at an arbitrary cycle, an example. We did some detailed numerical calculations. We looked at the Otto cycle, which is a spark ignition or a representation of a spark ignition cycle, primarily gasoline. So we got the Otto cycle, which mimics the gasoline engine as far as blackboard and thermodynamic work is concerned. So today we're going to look at the diesel cycle. Diesel cycle is a bit different than the Otto cycle because the method by which the fuel is burned and therefore the heat is added is a little bit different. So we're going to change one of the processes compared to the Otto cycle to achieve a diesel cycle. And then we're going to shift gears and look at an open system air standard cycle, so referred to as the Brayton cycle. So we're going to look at the Brayton cycle, which is an open system air standard cycle. This cycle mimics or is similar to a gas turbine, jet engine as well. So the Brayton cycle is used as an idealized, i.e. for blackboard thermodynamic work, an idealized either jet engine cycle or a gas turbine cycle. So we'll talk a little bit about the Brayton cycle today. We'll derive the efficiency of the Brayton cycle, get an expression for the Brayton cycle efficiency, basically W dot shaft divided by Q dot N. That'd be the definition of the efficiency for an open system. Open system here is going to be using shaft work as the output. And then we'll see if we can do a little example, or at least get started on an example involving a Brayton cycle. Okay? Indeed, we'll relax some of our assumptions about internally reversible processes. We'll deviate a little bit away from the air standard assumptions, and we'll assume that the compressor and turbine in the open system Brayton cycle are not 100% efficient, isentropic efficient. There'll be some irreversibilities in the cycle. So that'll be a little bit different today. Okay? So let's talk for a moment here about spark ignition versus compression ignition in internal combustion engines. So we have spark ignition. So we have spark ignition. This is gasoline. Gasoline engines use spark ignition to a spark to ignite the air-fuel mixture. So at top dead center, so here at top dead center, we have the piston here. So we have air and fuel. So we are at top dead center. So the piston is as far up as it's going to go on the compression stroke. Isentropic compression, if you like. And we have a little spark up here, a little spark plug. So here's our little spark plug up here. Spark plug. And a little spark occurs. So a little spark occurs, and the air and fuel start to burn. Now the air and the fuel burn so quickly that we can model the reaction and therefore the heat addition as one of constant volume heat addition. So we have fast combustion from a spark. Spark basically nearly instantaneously burns the air-fuel mixture, so we have a fast combustion process. So we modeled it as isobaric heat addition. Okay, so that's what happened with the spark ignition or gasoline engine. Very fast combustion process, faster than the rate at which the actual engine is turning in terms of RPM. The combustion process is much faster than the speed of the engine, so we assumed it was constant volume combustion. For compression ignition engines, compression ignition, So this would be the diesel, for example. Diesel engine. The fuel is injected by a mechanical fuel pump. So here we are around top dead center. So instead of having an air-fuel mixture pre-mixed and ready to explode, we simply have air. We simply have air, not fuel, just air. And we have a fuel injector. So we have a little fuel injector here. So there's a little passageway here. And we are squirting fuel. Fuel injection. Okay, so we're squirting fuel into this highly compressed, high pressure, high temperature air near top dead center. And the fuel burns as it is injected. So fuel injected slowly. It's injected by a mechanical fuel pump. It's not injected all at once. It takes time. So fuel is injected slowly. Therefore, it burns slowly. Therefore, instead of assuming a constant volume, isochoric heat addition processes in the Otto cycle, we're going to assume a constant pressure heat addition process. Burns slowly, so we're going to assume that the heat addition process, i.e. the heat release during the combustion or the burning of the injected fuel, we're going to assume this is a isobaric heat addition process. Isobaric, constant pressure heat addition process. Everything else is the same as the Otto cycle. It's just we're changing the heat addition process. Just changing the heat addition process. So let's have a look here at the diesel cycle. Diesel cycle, air standard diesel cycle. So let's put up the TS and the PV diagram here. So here we have PV, and here we have TS. PV and TS. So process 1 to 2, adiabatic compression. Remember, the air standard cycle assumes reversible, internally reversible processes. No irreversibilities inside the piston cylinder device. No friction, no unrestrained expansion, no heat transfer inside the piston cylinder device across a finite temperature difference. So we're going to start off at state 1. So state 1 is the highest volume state, and we're going to adiabatically compress the air. Remember, in the diesel cycle, we don't have an air-fuel mixture pre-mixed and ready to burn. We have air and we inject fuel when we want to start the heat release or the burning process. So for the Otto cycle, we start off with already mixed air-fuel mixture, and then we initiate a spark and the heat is released essentially all at once, very rapidly. So we approximate this as an isochoric heat addition process. But for the diesel, we start off with compressed, i.e. very hot, high pressure air, and then we inject fuel via a fuel pump with a fuel injector into the combustion chamber, into the hot air, and it starts to burn as soon as it hits that hot, highly compressed air. But it burns at a rate fairly slowly because we're limited by the rate in which the fuel can be injected by the fuel pump. And the fuel pump slowly injects fuel. So we assume that this is an isobaric heat addition process for the diesel, as opposed to an isochoric heat addition process for the gasoline or Otto cycle. Okay, so process 1 to 2 is adiabatic, internally reversible, therefore isentropic. So State 1 starts right here, and we have isentropic compression up to state 2. Temperature goes up because volume is going down. We're doing work, boundary work on the air, and it's starting to heat up. That's why temperature goes up from 1 to 2. Pressure goes up, volume goes down. Remember, we have a Vmax and a Vmin in the cycle, just like we did in the Otto cycle. But now, instead of having isochoric heat addition, we have isobaric expansion with heat addition. So we begin to expand. We begin to expand the air, and we add heat at the same time. So Q in occurs from state 2 to state 3. Okay, so we're adding heat isobarically. So that's a horizontal process on the PV diagram. Temperature goes up and entropy or specific entropy go up because we're adding heat. So now we have a temperature increase as we add heat and an entropy increase as we add heat. So delta S is positive from 2 to 3. From 2 to 3, okay? Then from 3 to 4, we have adiabatic expansion. We turn off the heat addition, and we allow the products of combustion or the hot air to expand out to state 4, and we allow it to occur adiabatically. If it's adiabatic and reversible, it's isentropic. So on the TS diagram, we have a movement vertically down, constant entropy down to state 4. And then we finish off the cycle back to state 1 with isochoric heat rejection, just like in the Otto cycle. So we have a constant volume, Q out, heat rejection, entropy decreases, temperature decreases, and we end up back at state 1. Okay? So the work producing cycle here takes heat isobarically, converts some of it into work, boundary work in this case, and rejects the heat isochorically. PV diagram is quite informative because that tells you the various processes. TS diagram tells you where the heat addition is occurring. Okay, that's pretty nice too. All right. Now, I'm not going to go into much detail here. We're not going to derive the efficiency for the Otto cycle assuming constant specific heat, but I will write down the expression and talk about it. You can look, there is a separate section in the notes just on the derivation for efficiency for the diesel cycle. It requires a little bit more work because the process is a little bit more complicated. In particular, there is a second volume here. Remember, for the Otto cycle, the efficiency was a function of the compression ratio alone. So we still have the compression ratio here. We have R is equal to Vmax over Vmin. We still have the compression ratio. We still have the compression ratio. And for the Otto and the diesel cycle, the higher the compression ratio is, the more efficient the device is. But we have another volume here. We have this V3 volume. This is the volume at which the heat addition stops. So not only do we have Vmin and Vmax in the cycle, but we have this other volume that describes the heat addition process or how extensive the heat addition is. So we have this other volume here, V3. And for the diesel cycle, V3 is the cutoff volume. Is the cutoff volume. So that's the volume at which the heat ceases to be added during the isobaric heat addition process. So V3 is called the cutoff volume. And we have another ratio, RC, which is the cutoff ratio, and it's defined as the ratio V3 over Vmin. or if you like, V2. So this is called the cutoff ratio. So not only do we have the compression ratio, but we have the cutoff ratio as well that describes the diesel cycle. So in the expression for efficiency for the diesel cycle, you have a complicated relationship between the compression ratio and the cutoff ratio, which give you the efficiency of the diesel cycle. Let me write down the efficiency of the diesel cycle for you. I don't memorize this stuff, so let's see here. Eta for the diesel cycle is 1 minus, and it starts looking a little bit like the Otto cycle. So I have a 1 minus 1 over K, and then I have 1 over the compression ratio, R, to the K minus 1 power. Now that looks exactly, with the exception of the 1 over K, it looks exactly like the Otto cycle efficiency. The Otto cycle efficiency was 1 minus 1 over K minus 1. So we got this K in here, that's a little bit more complicated. And then we have in parentheses here, we have the cutoff ratio to the kth power minus 1 divided by the cutoff ratio minus 1. So we have this additional term here that makes the expression for the diesel cycle efficiency a bit more complicated. And it's because you've got this additional parameter dictating what the heat addition is. And we see that the efficiency has to do with the amount of heat being added. Okay? Now, one thing to note, as R sub C goes to 1, then this term goes away. So as R sub C goes to 1, in other words, V3 goes to V min. In other words, we don't add a lot of heat. So note, as Q in goes to 0, R sub C goes to 1. And with the exception of this 1 over K right here, the efficiency of the diesel becomes similar to the Otto cycle. I will put similar to. We got this 1 over K in here, so it's not quite the same, but as R sub C goes to 1, this term goes to 1. Forget the 1 over K for a minute, but we have this compression ratio term. So the diesel cycle efficiency becomes similar to, not the same because we got this 1 over K, becomes similar to the Otto cycle efficiency. Similar to, that's what this tilde means. Now, why are diesels so popular in many applications? Well, they're very popular because they're often extremely efficient. Why is that true? Why are they extremely efficient? Well, for one thing, so advantage of diesel cycle. The primary advantage for the diesel cycle, pretty much the only advantage, I guess, is you can have much higher compression ratios. So R for diesels, much higher, often much higher than Otto cycle. Remember I was saying for Otto cycles, R for Otto cycles, the compression ratio, usually around 10 to 12, usually around 10 to 12. That's the compression ratio for Otto cycle engines with spark ignition, okay? And as I discussed last time, we can't really get a lot higher than that because if you pre-mix the air and the fuel together, and you increase the compression ratio too high, you'll get uncontrolled combustion that causes knocking. Anything higher than around 12, direct injection is helping with that a little bit, but anything higher than 10 to 12 and you start getting knocking, okay? You can use higher octane fuel. Higher octane fuel is more resistant to knocking, but highest compression ratios for Otto cycle are around 10 to 12. On the other hand, for diesels, where you're compressing air, not air fuel, you don't have this inherent problem with knocking. The rate of heat release is controlled by the injection rate for the fuel, and we have pretty good control over that. So knocking is not really a problem, a technical problem for diesel development, so we can crank up the compression ratio quite high. And notice here that as the compression ratio gets very high, this entire term gets very small, and the efficiency of the diesel cycle goes to the efficiency of 1. Very high efficiencies are possible with a diesel because we can crank up the compression ratio. For most diesels, R for diesels usually range anywhere from around 16 all the way up to 22. Very high compression ratios. You got yourself an old indirect injection diesel, like from a Mercedes from the 80s or the 70s, you're looking at a compression ratio of about 21.5 to 1 or 21.5. Very high compression ratios are possible with diesels. Therefore, efficiency of the diesel is usually greater than the efficiency of the Otto cycle because you can get such a high compression ratio, okay? You can't get too high or you start having mechanical problems. You'll end up getting very high friction. You have very high compression ratios and pressures. You have to make the engines very bulky, heavy to withstand the forces associated with those high compression ratios and high pressures. Okay, so the primary advantage of the diesel is we can have higher compression ratios and therefore higher thermal efficiencies for the diesel cycle. A good diesel cycle will probably get around 30 to 40% thermal efficiency. A good Otto cycle will probably get around 20 to 30, maybe 30. Those numbers are going up with recent technological advances and the use of direct injection in gasoline engines as well. Gasoline engines are typically now going towards the diesel cycle, even though they use gasoline, and they're able to do that because they can inject. They're developing high pressure pumps and high pressure systems for injecting gasoline. So gasoline engines are actually going more towards the diesel cycle with the use of high pressure direct injection for gasoline engines now as well, okay? Okay, I think that's enough about the diesel cycle. You can read the section on the diesel cycle, and in the homework, you'll probably have a diesel cycle to analyze. Once you do one cycle analysis, you've done them all. We've already done one detailed cycle analysis problem. That was in the early part of the chapter a few days ago. So once you've done one cycle, you pretty much have done them all. Just the processes are a little bit different, okay? All right, let's take a break for a second here, and we'll move on to Brayton cycles. Okay, let's look at an open flow device, not a closed system, but an open device that produces work, and that is called the gas turbine. The gas turbine is modeled as a Brayton cycle. Brayton cycle is used to represent a gas turbine. So how does a gas turbine work? Well, it uses one compressor, or perhaps multiple compressors. We'll talk about that later. It uses a compressor to pressurize air. So air is inducted into a compressor. It is then compressed up to state 2. If this is the ideal Brayton cycle, the compression occurs reversibly and adiabatically. So let's draw the TS diagram here. So let's draw the TS diagram as we go along. We start off at state 1. And then if we're dealing with the ideal Brayton cycle, we have reversible compression up to state 2. In the compressor. And then the compressed air is then fed into a combustor, which is approximately an isobaric device where fuel is injected and then burns. So this is a heat addition process occurring inside the combustor. And so we're modeling this as an isobaric heat addition process. So we have heat addition going on, Q inside the combustor. I'm calling it Q combustor. It's really Q in. Okay, up to state 3. Heat addition up to state 3, and that's an isobaric process. And then, so that brings us to state 3, isobaric compression in the combustor. And then we have expansion in the turbine where the work is extracted. Energy is extracted from the flow, producing work. And so if this is an ideal Brayton cycle, we have reversible expansion in the turbine. So pressure and temperature fall, assuming it's an adiabatic turbine. Pressure and temperature fall, and we end up at state 4. So we exit the turbine. Now, how does this device actually produce power? Well, some of the power produced by the turbine. The turbine's producing power, and the compressor is consuming power, okay? Some of the power produced by the turbine is fed in to drive the compressor, and the remaining power left over produced by the turbine, the net power, W dot net, which is the difference between the turbine and compressor power, that is your net power output for the gas turbine. So it's critical to understand here. Some of the power produced by the turbine, W dot turbine, is fed into and drives the compressor, and the remaining, what's left over, W dot net, is the net output for the gas turbine, okay? The heat rejects, so the exhaust at state 4 is then rejected into the environment. The environment basically is at constant pressure, 1 atmosphere or something like that. So the heat rejection process is assumed to be isobaric. So we have Q out. We're not really interested in Q out too much. Q combustor or Q in is what we're really interested in. So let's go over the characteristics of the ideal Brayton cycle one more time. It uses a combination of open flow devices, compressor, combustor, and turbine. The turbine drives the compressor, and the net work is W turbine minus W compressor, or W dot. If this is an ideal Brayton cycle, the compressor and turbine operate reversibly as well as adiabatically. The heat addition process in the combustor is isobaric. So we're injecting fuel into a chamber. The fuel is burning, releasing heat, and it's assumed that that occurs isobarically or nearly so. And then we have isobaric heat rejection going on in the environment. So those are the characteristics of the Brayton cycle. Those are the characteristics of the Brayton cycle. So let me write these one more time over here. We'll write it over here. So again, for the ideal Brayton cycle, compressor, turbine operate reversibly, constant pressure heat addition and rejection process. We have process 1 to 2, which is adiabatic, and therefore adiabatic reversible, and therefore isentropic compression. So it's reversible, adiabatic, therefore isentropic. And then from 2 to 3, we have isobaric Isobaric heat addition in Combustor from 3 to 4, we have adiabatic expansion, and it's reversible in the turbine. So this is the compressor, and this is in the turbine. And then we have isobaric heat rejection going on in the environment. Isobaric heat rejection in environment. Okay, so we're modeling this as an isobaric heat rejection to the environment, okay? Into the environment. Now, this idea of having reversible compressors and turbines. So the idea is not only are these adiabatic here, but they're reversible and therefore isentropic. Not really very realistic. Let's try to inject a little bit of realism here into our Brayton cycle. Make it more realistic. So there's the non-ideal Brayton cycle, which allows for inefficiencies, irreversibilities in the turbine and compressor, and maybe if you want to get really adventuresome, a pressure drop in the combustor. Pressure drop occurs due to the acceleration of the flow as it gets heated up. As you heat something up, the density goes down and the flow velocity has to increase to maintain m dot. There's also maybe some friction going on in here. So we may have a pressure drop in the combustor. We certainly have possibly inefficiency in the turbine and compressor. So for the non-ideal Brayton cycle, we have efficiency for the turbine and the compressor. So eta turb and eta compressor, these are isentropic efficiencies. These might be not equal to 1, or I guess I'll just say they could be less than 1. So in other words, irreversible. We might have irreversible turbine and compressor operation. We also may have pressure drops across the combustor. Could be a delta P across the combustor, COMB, delta P across the combustor. Let's see here, the combustion occurs. The combustion in the combustor occurs from state 2 to state 3, the heat addition in the combustor. So there might be a delta P, which is P3 minus P2. So that may not be, that may be less than 0. So there might be a pressure drop across the combustor. Might be a pressure drop across the combustor. So these are all possibilities. How does this change our TS diagram? How does this change our TS diagram? For a more realistic gas turbine involving the possibility of pressure drop in the combustor and inefficiencies in the turbine and compressor. So again, we'll start off at state 1. So here's state 1 right here. Now, let me put in the isobars. Let me put in the relevant isobars here. In fact, I think, let me go back here and make sure the isobars are included. Let's put, so this is our P max, maximum pressure isobar. Here's our P min isobar. Let me put some of these isobars into our TS diagram. So we have our P min, we have our P max. There's our P max isobar right there. Let's see here. The reversible compression from state 1 to state 2 would look something like this. So here's 2 sub S. This is the isentropic compression process, but we don't have an isentropic compression process. We have a process involving some delta S. So here's state 2 right here. There's 2 sub S, that's the isentropic. That helps us define our isentropic efficiency. We've done this stuff before in the chapter on entropy when we talked about turbines and compressors. Then we have maybe a pressure drop. So here's P max is equal to P2, and here I have P3. There's our P3 isobar. So we have a pressure drop. We start off at a high pressure P max, and then we drop to a lower pressure in the combustor. And so this is state 3 here. There's state 3. Delta P across the combustor, delta P. And then we have the isentropic expansion process. So this is to 4 sub S. But the real turbine has some inefficiencies. So state 4 is actually a little bit to the right, okay? So we have the heat addition process going on here in the combustor, Q combustor, and then we have the heat rejection process going on there. So the ideal process would have vertical lines for the compression and expansion process in the compressor and turbine. The real processes have a delta S because they're irreversible. And then we maybe have a pressure drop in the compressor and the combustor. In the combustor, maybe. So that's what the TS diagram looks like for a non-ideal Brayton cycle. If you want to know what the expression for efficiency of a Brayton cycle is, note the expression for the efficiency of a Brayton cycle, assuming constant specific heats, 1 minus 1 over R sub, let's see here, let me make sure I'm using the right notation here. Remember, R is a compression ratio in our, in our closed systems, Otto cycle, diesel cycle, whereas, R sub P. R sub P, K minus 1. Now, what's R sub P here? R sub P is the pressure ratio. So it's P max over P min. Pressure ratio. So the efficiency for the Brayton cycle, 1 minus 1 over RP, pressure ratio, K minus 1 in the exponent. What this means is as the pressure ratio goes up and the maximum pressure gets higher and higher, we squeeze the air down as it goes through the compressor more and more, do more compressor work. As the pressure ratio goes up, this term goes to 0 and efficiency approaches 1. So the idea here is, as the pressure ratio goes up, so note, as the pressure ratio goes up, the efficiency of the Brayton cycle also goes up. Currently, pressure ratios, depending on the engines, are about 30 or so. So in the gas turbine that you see on the airplane that you ride, so the airplane usually utilizes a Brayton cycle, a gas turbine. It's going to be on the order of 30 or more, 30 or more. So pressure ratios have been going up and up and up to increase efficiency, okay? Now, I'm not going to go through the derivation of this expression. What I invite you to do is note that this actually looks a lot like the Otto cycle, except it's constant pressure heat addition and rejection instead of constant volume heat addition and rejection. Go through and look at the derivation for the efficiency of the Otto cycle and see what changes if we have constant pressure heat addition and rejection instead of constant volume. The answer is almost nothing changes. The only difference is you'll have a CP instead of a CV at some point when you calculate the heat addition. The CPs and the CVs cancel out and you get exactly the same expression, the exact same development for deriving the efficiency of the Brayton cycle as for the Otto cycle. So I'm not going to go through the derivation of the Brayton cycle efficiency. I do want to hold you accountable for it, so why don't we put a box around it? Because the derivation is exactly the same as for the Otto cycle. No difference, and the equation is the same, except this is a pressure ratio instead of a volume ratio. Okay, so I'm not going to go through that derivation. All right, let's take a break for a moment. Let's do an example involving a non-ideal Brayton cycle. Let's do an analysis here. Okay, so let's do a little example here involving a non-ideal Brayton cycle. So remember, the Brayton cycle utilizes a compressor which compresses the air, a combustor where the heat addition occurs, perhaps isobarically, perhaps not, and then work is extracted by the turbine, and some of that work or power is used to drive the compressor, and the remaining, or what is left over, if we subtract the compressor power or specific work, is the net work produced or net power produced by the gas turbine. This whole thing is the gas turbine. So let me put up the TS diagram here. Well, let's go over the givens first. So we have an inlet temperature into the compressor, T1. We have a pressure ratio, a compressor pressure ratio, the ratio of P max over P min, or if you like, P2 over P1, that's the pressure ratio, and is 8. So the compressor pressurizes the air by a factor of 8 in terms of the ratio of inlet to outlet pressure. The maximum temperature, presumably that occurs after the combustor, so that's T3. The maximum temperature is 900 degrees Kelvin. So we heat up the air by up to 900 degrees Kelvin. The net power produced by the gas turbine, the total power produced by the gas turbine is 15 megawatts. And the isentropic efficiencies for the compressor and the turbine are 80 and 86% respectively. These are not isentropic turbines and compressors. Okay? Now let's make a few assumptions here. I don't see any actual explicit statement, but let's assume that there's no pressure drop across the combustor. I don't see that there's a delta P across the combustor in the given. So I'm going to write here, I'm going to assume isobaric combustor. Isobaric combustor. I also don't see it, but I'm going to assume it. I'm going to assume adiabatic, compressors, and turbine. I don't see anything here, but there's really no way to calculate the heat rejection or addition in the turbines and compressors. I have no information, so I'm going to assume adiabatic compressor and turbine. Okay, adiabatic compressor and turbine. We'll move on from there as we need to. Let's draw the TS diagram, therefore, for this process, for this device. So we have a state 1 is the inlet. Let me put in my P min. Let me put in my P min and my P max isobar. That doesn't look good. So here's my P min, and here's my P max. P min and P max isobar. So we're compressing in the compressor, the air starting off at state 1. The isentropic process, if this were an isentropic compressor, this would be state 2 sub S. Sub S means constant entropy. But we have an isentropic efficiency less than 1. So we're going to have some irreversibility inside of the compressor, and therefore some entropy generation, and therefore a delta S within the compressor. So this is state 2, an increase in entropy from state 1 to state 2 because we have irreversibilities occurring inside the compressor. Then we have apparently, isobaric heat addition in the combustor. So we have Q combustor, isobaric. We don't have a delta P across the combustor. Up to state 3, and actually we have temperature T3. That's our maximum temperature. So let me put up the initial and final and maximum temperature, the low, the minimum, and the maximum temperature here. So this is 310 degrees Kelvin. That's the minimum temperature, and the maximum temperature is 900 degrees Kelvin in the cycle, okay? Min and max temperature. And then we have expansion in the turbine. It's going to be irreversible, so there's going to be a delta S compared to the isentropic expansion process. So we expand from state 3 to state 4. There's a positive delta S because we have entropy generation, and therefore delta S is positive through the turbine. And then we have the heat rejection process going on in the environment, okay? All right, so let's get started here. Let's calculate the net power or net work. Looks like a lowercase w net, so I want specific net work, so analysis. I guess I want to erase this too. So this is a non-ideal Brayton cycle. No pressure drop across the combustor, so that simplifies things a little bit. So I want to find W net. Now, W net is the difference between the turbine and compressor power, or work per unit mass. So assuming the m dot is all the same throughout the cycle, then the difference between the compressor and turbine power is the net. Okay? So let me write here, W dot net is equal to W dot turbine minus W dot compressor. Now, if I divide everything by m dot for the air, and we assume m dot for the air is constant, m dot's constant throughout the cycle, then I get W net is equal to W of the turbine minus W of the compressor. So I need to find the compressor and turbine specific work, and then I'll have W net. Okay, well, let's find the compressor specific work first. So let's look at process 1 to 2. That's compression in the turbine, in the compressor. Compression. That's the compression process in the compressor. So if I apply the energy balance, to my open flow compressor, it's adiabatic. Work is positive, compressor work is positive on the system, not by the system. And if I assume no changes in kinetic and potential energy, I got no information about kinetic and potential energy of any of the flows in this device. So I think I'm going to say delta KE equals delta PE 0 for every device. So I'm going to neglect kinetic and potential energy in the energy balance. If I do all that, I get a open system entropy, open system energy balance yielding W dot compressor is equal to M dot H2 minus H1. Now I can divide both sides by M dot, and I get specific compressor work is equal to H2 minus H1. Now I know H1, but I don't know H2. I need to know a temperature at state 2 or something. All I know is the pressure. I need a temperature to go to a table and extract out H2. So I don't know what this is. And frankly, there's no way to get it. Okay? So this is not going to help. This is not going to help. Let's do the following instead. Instead of looking at process 1 to 2, let's look at process 1 to 2 sub S. Process 1 to 2 sub S. This is the isentropic compression process. Let's look at 1 to 2 sub S. Now, why would I be interested in looking at 1 to 2 sub S? In other words, the reversible compressor? Because this isn't going to help me, but this will. The definition of isentropic efficiency of a compressor is W dot of the isentropic compressor divided by W dot for the actual compressor. Of course, I can divide this by mass flow rate and I get W isen compressor divided by W compressor. And therefore, the real compressor work, W compressor, is equal to the isentropic compressor specific work divided by the isentropic efficiency. Now, I have the isentropic efficiency. I don't have the isentropic specific work for the isentropic compressor, but maybe I can get it. So let's look at process 1 to 2, which is the process for the isentropic compressor. If I apply the energy balance, I get W isen compressor is equal to H2 sub S minus H1. That's from the energy balance. No change in kinetic and potential energy, no heat transfer, steady state. It's all steady state. Okay, so I know H1. I don't know H2 sub S. So H2 sub S is equal to H2 is equal to H evaluated at a pressure P2 and S2 sub S equals S1. So it's an isentropic compression process where pressure is equal to P2. Well, if this is an isentropic compression process, then it means that PR2 sub S over P1, PR1 is equal to P2 over P1. If you want to be cranky here, I can do a P2 sub S, but P2 sub S is just the maximum pressure P2. So this is P2 over P1. Now P2 over P1 is our pressure ratio. P2 over P1 is our pressure ratio. P2 over P1 is R sub P, or our pressure ratio across the compressor. So this is R sub P. Let me put up the TS diagram while we're doing this, just to make sure that we're all on the same board. So this is P1. This is P2. This is state 1. This is 2 sub s. And this is the actual compression process, 1 to 2. Okay? So that's what's going on right here. So we're looking at 1 to 2 sub s. 1 to 2 sub s, which is isentropic. Okay? Okay, so this means that P R2 sub s is equal to PR1 times the pressure ratio. Let's see here, PR2 sub s, what is that? Not a lot of room here. I'll write it right over here. PR2 sub s is PR evaluated, I'm sorry, PR1. PR1, let's find PR1. PR1 is PR evaluated at T1, which is 310 degrees Kelvin. 310 degrees Kelvin. T1 is 310 degrees Kelvin. Going to tables, PR1 is 1.55. 1.55. Maybe I can get a couple more decimal places there. And that's from IGB tables, 1.555. Okay, so 1.555, the pressure ratio is 8, and I get a PR2 sub s. PR2 sub s equal to 12.44. 12.44. 12.44. So PR2 sub, so H2 sub s, so this is H evaluated at PR2 sub s, which is 12.44. And I look up H at PR2 sub s of 12.44. And I get H2 sub s 562. 562. 562 kilojoules per kilogram. Okay, so now I have H2 sub s. Let's see here. Oh, what's H1? I don't have an H1. Let's see here. Do it over here. H1 is H evaluated at T1, which is 310 degrees Kelvin. Should be about 310 kilojoules per kilogram. Let's see here, 310 kilojoules per kilogram. And that's from IGB tables. IGB tables. Okay, so W Isen compressor is 562 minus 310 kilojoules per kilogram. And I get an isentropic compressor work. Isentropic compressor work per unit mass of 562 minus 310, 222 kilojoules per kilogram. So that's the isentropic compressor work. Okay, so I now have the isentropic compressor work. Let's see here, 222 kilojoules per kilogram. And then I divide that by 0.8. The compressor isentropic efficiency is 80%. 80%. And I get a specific work for the compressor. Specific work for the compressor, whoops, divided by 0.8 of 277. Oh, running out of room. 277 kilojoules per kilogram. Kilojoules per kilogram. Notice that the isentropic compressor takes less power than the real compressor to pressurize the flow up by a factor of 8. Okay? So let me write this somewhere. So W compressor is 277 kilojoules per kilogram. All right. I'll write that somewhere. I need to write that somewhere. Okay. All right. So now we need to find W turbine. We need to find the turbine specific work. So let's look at process 3 to 4. Let's look at process 3 to 4. Process 3 to 4. This is expansion in the turbine. Again, if I write the energy balance, I'm going to get W turbine is equal to H3 minus H4. Assuming no heat transfer, steady state, steady flow, no changes in kinetic and potential energy. I know H3. How do I know H3? Because I have the temperature. I have the maximum temperature at state 3. Let's actually see if we can crank that out. So I know H3, T3, 900 degrees Kelvin is the maximum temperature in the cycle. So I can get H3. So I do know H3. I do know H3. Let's see here. H3 equals H evaluated at T3, which is 900 degrees Kelvin. And I can crank that out pretty quick. From tables, let's see here. H3. It's in here somewhere. Yes, 932 kilojoules per kilogram. 932 kilojoules per kilogram. Okay, I get that from tables, no problem. So I know this. I don't know H4. I know the pressure, but it's an irreversible turbine, so it's not a constant entropy process. So this, I don't know H4. This doesn't get me anywhere. So I can't do this. Like with the compressor, I can't do this. But I can use the definition of isentropic efficiency. So efficiency for the turbine, isentropic efficiency, is defined as the actual work from the turbine divided by the isentropic work of the turbine. I'm running out of chalk here, okay? In other words, dividing by m dot, W turbine is equal to eta turbine times the isentropic turbine specific work. Now, I know the efficiency for the turbine, it's 86%. 86%. So now I need to evaluate the isentropic turbine work. So let me put up the TS diagram for the turbine. So here's S, here's T, here are my, it doesn't look good. Here are my P-min and P-max isobars. So here's state 3. The isentropic turbine goes down to 4 sub S. The real turbine, the actual turbine, increase in entropy goes to state 4, okay? So process 3 to 4 sub S, this is isentropic turbine work. So again, energy balance, I get W turb isen equals H3 minus H4 sub S. H3 I've got 932. I need H4 sub S. How do I get H4 sub S? Well, PR4 sub S over PR3 is equal to the pressure ratio, P4 over P3, or if you like, or if you like, this is P4 is the minimum pressure, and P3 is the maximum pressure. So this is 1 over the pressure ratio. Okay? Isentropic process. So PR4 sub S is equal to PR3, 1 over the pressure ratio. So what's PR3? Let's see here. PR3 is PR evaluated at T3, which is 900 degrees Kelvin. Let's see here. What's PR3? I can get that from a table. PR3. 75.3. 75.3. And that's from a table. Okay. So I get 75.3 times 1 over 8. So let's divide that by 8. And I get PR4 is equal to 9.4. 9.4. So H4 sub S is H evaluated at P4R4 sub S, which is 9.4. So H4 sub S I can get out of a table, and I get 519.32. 519.32 kilojoules per kilogram. Okay, I have H3, I have H4. So I've got 932 minus, I'll just do 519. 519 kilojoules per kilogram. And I have the specific work for the isentropic turbine, the most efficient one. The most efficient one, I guess I better crank this out. 932 minus 519, or 413 kilojoules per kilogram. Okay? So the work for the turbine is the isentropic efficiency, and that is 86%. So 0.86 times the specific work for the isentropic turbine. So 86% of 413. I get 355. 355 kilojoules per kilogram. So the specific work for the turbine is 355 kilojoules per kilogram. Okay? 355 kilojoules per kilogram. Okay, now I know the net work. So 355 minus 277. The net work is only 78 kilojoules per kilogram of airflow through the compressor and turbine. Okay? 78. So the net specific work is 78 kilojoules per kilogram. That's it. The compressor power is 277. Compressor work, sorry. So W compressor is 277 kilojoules per kilogram. And of course, the turbine work is 277 plus 78, which was 355. Okay, so let's box this up somewhere. So W net is 78 kilojoules per kilogram. So let's box this up somewhere, okay? That's W net. Okay, let's calculate this thing called the back work ratio. The backwork ratio gives you an idea of how much power is required to run the compressor compared to the power produced by the turbine. In fact, it's the ratio. It's W dot compressor over W dot turbine. Backwork ratio. Backwork ratio. W dot compressor over W dot turbine. Backwork ratio. Back work ratio equals W dot of the compressor divided by W dot of the turbine. And we can divide top and bottom by M dot for the air. In fact, I had to write the assumption down here. We are assuming that the airflows are the same throughout the device. So I'm going to write here M dot equals M dot air for all devices. Why might that not be true? Why might the mass flow be different in the real world in these devices? The reason is because we are adding fuel and therefore heat. Q dot combustor. We're actually adding fuel into the combustor, not very much. By mass, maybe 1 or 2% of the airflow. We're adding a little bit of fuel and we're burning it. So the mass flow rate through the turbine is a little bit larger than the mass flow rate through the combustor, but we're not through the compressor, but we're not worried about that. We're not worried about that. We're going to assume the mass flow rates are constant. Okay? So I'm going to divide top and bottom by M dot air. Okay? And I get W compressor over W turbine. Well, I've got W compressor, that is 277 kilojoules per kilogram. And I got W for the turbine, which was 355 as I recall. 355, yep, kilojoules per kilogram. These cancel out, and I get a backward ratio, 277 over 355. 277 over 355, I got it. Let me crank it out in my calculator. Probably about 80%. Almost 80%. 78%. Okay, 0.78, 78%. Three quarters of the power produced by the turbine gets used to drive the compressor, only leaving a quarter left over. Okay, so that's my backwork ratio. Let's see, so let's put that in a box over here. Backwork ratio. Clearly, the higher the you want a fairly low backwork ratio. Backwork ratio 0.78, or if you like, 78%. Clearly, you want a gas turbine with a fairly low backwork ratio. And you do that by improving the efficiencies of the turbine and the compressor. Okay, what's next? We're supposed to calculate M dot for the air. How much air is flowing through the device? So I wanted to know what M dot air is. Okay. So I want to know what M dot of the air flowing through the gas turbine is. So I want to know what the M dot is flowing through here. Now, luckily, we know what the net turbine work is. It's 15 megawatts. So actually, W dot net is 15 megawatts. Okay? W dot net is 15 megawatts. So let's write W dot net, which is, by the way, equal to W net times M dot for the working fluid, which is air, is equal to 15 megawatts. Okay, so I've got this. I've got W dot net. Okay, so let's solve for M dot air. M dot air is equal to W dot net divided by the specific net work. let's see here. So we have 15 megawatts. The net work was 75 kilojoules per kilogram. No, I'm sorry, 78 kilojoules per kilogram. I got to convert kilojoules into megajoules. Oh, let's see here. So there is, for 1 megajoule, I got 1,000 kilojoules. Okay, so we have some unit conversion there. The kilojoules cancel out, and I have a megawatt, a kilojoule, and a kilogram here. The kilograms go upstairs. A megawatt, by the way, is a megajoule per second. So I'll end up with kilograms per second, which is a unit of mass flow. Let's see here. What have I got? What do I do with my calculator? Where is my, here it is. So 15 times 1,000 divided by 78. And I get 192 kilograms per second. 192 kilograms per second. 192 kilograms per second of air. That's a lot of air. That is a lot of air. Okay? So m dot, 192 kilograms per second. 192. Let's see here. (192 kilograms per second). So m dot, 192 kilograms per second. 192 kilograms per second. Okay, there we go. Okay, so let's move on here. Let's move on. Let's now calculate the heat addition. Let's calculate Qin. Let's calculate Qin. Qin, or Q in the combustor. If I apply an energy balance to the combustor, so I apply an energy balance to the combustor, no changes in kinetic and potential energy, no work interactions, I get H3 minus H2. I already have H3, I calculated that previously. I don't have H2. H2 is the compressor exit enthalpy, specific enthalpy. So let's look again at process 1 to 2. Process 1 to 2. So here's my TS diagram. TS. Here's my min and max isobars. Here's the isentropic process. Here's the real process in the compressor. Okay? And if I apply the energy balance, I get W compressor is equal to H2 minus H1. So W compressor is equal to H2 minus H1. H1 I have, the compressor work I have, so I get H2 is equal to work compressor plus H1. Let's see, the compressor work, specific work was 277 kilojoules kilojoules per kilogram, and then H1 was 310 kilojoules per kilogram, and so H2 is equal to 587 kilojoules per kilogram. So now I have H2. H3, what was H3? As I recall, that was H at temperature T3, which was 900 degrees. So I get 932 kilojoules per kilogram. 932 minus H2, which is 587 kilojoules per kilogram. And I get heat addition. Heat addition is 932 minus 587, or 345 kilojoules per kilogram of airflow. So let me write what my Q dot is in the combustor, my Q in the combustor. So Q combustor is 345 kilojoules per kilogram. Okay, 345 kilojoules per kilogram. Okay, so let me write it here. Q combustor, 345 kilojoules per kilogram. I'm going to box that up too. A lot of stuff to calculate here. A lot of stuff to calculate. So that's the Q in as my Q combustor. Okay, let's calculate the efficiency. Well, this is easy to do. Efficiency is just W dot net over Q dot in. So the efficiency of this thing, this Brayton cycle, equals W dot net over Q dot in. So if I divide by the mass flow, I get W net, because the mass flow is the same everywhere, Q in, and my Q in is my Q combustor. So I get W net over Q combustor. Oh, what was my W net again? 78 kilojoules equals 78 kilojoules per kilogram. And then Q combustor was 345 kilojoules per kilogram. Let's calculate that. And I get 22%, or 22.6%. Okay? So the efficiency of this device, the thermal efficiency of my Brayton cycle here is about 22%. So eta 22.6%. Okay. 22% of the energy added to my system or taken in by the system, the device is converted into usable work. Only a quarter. Let's compare that to the Carnot cycle. Let's say instead of having this thing here, this Brayton cycle with all these irreversibilities going on, what if we had a Carnot cycle doing the same thing? What if we had a Carnot cycle doing the same thing? So we have a Carnot cycle operating between a maximum temperature in the cycle, Carnot heat engine, and this thing is running all the time, rejecting heat at the lowest temperature in the cycle. So T min, T max and T min. T max and T min. So it's producing W dot, taking in Q dot high, rejecting Q dot low. Let's figure out what these min and maximum temperatures are in the cycle. So we're going to put a Carnot cycle between these min and max temperatures. Well, the maximum temperature in the cycle is 900, so the heat has to be received at least at 900 degrees Kelvin, and the minimum temperature in the cycle is 310, so the heat has to be rejected at least at 310 degrees Kelvin. So the min and the max are 900 and 310. So the efficiency of the Carnot, or if you like, the maximum efficiency of any heat engine operating between these two limits is 1 minus T min over T max, or T low over T high, which is 1 minus 310 over 900 degrees Kelvin. And you put that in your calculator. 1 minus 310 divided by 900, and I get 65%. So the Carnot heat engine would convert 2/3 of the energy received in the combustor to work. Our Brayton cycle there, with all of its irreversibilities, only converts 22%. So this guy only has a 22% thermal efficiency, whereas the Carnot, or the maximum efficiency, is 65%. Okay, it's due to the fact that the heat's being received at low temperature for much of the cycle, and we have all these inefficiencies going on in the turbine and compressor. Also has to do with the heat being rejected at temperatures other than the minimum temperature. And so that results in heat transfer across a finite temperature difference outside the device. Okay, we've calculated everything in sight on this problem. I hope you have a good handle on it. Take care, ladies and gentlemen. Actually, I was just about ready to erase everything, and I realized I made a small mistake on the compressor work, specific work calculation. I don't know how I made the mistake, but it's actually 315. I think I had put the wrong numbers in the calculator at some point. 315 kilojoules per kilogram. Well, that reduces the net work from 78 to 40 kilojoules per kilogram. So 40 kilojoules, not 78. That bumps up the backward ratio up to 80%. Because the specific work is lower, net work is lower, I have to increase the mass flow rate to get the same W dot net. So that almost doubled the mass flow rate up to 370 kilograms per second. Because the outlet has a higher enthalpy at the compressor, that means I don't have to add as much heat. So I end up with a higher specific enthalpy at the outlet of the compressor. So I don't have to add as much heat to get up to the maximum temperature. So Q combustor goes from what, 345 down to 307 kilojoules. And that changes my final efficiency to 13%. So 40 divided by 307, 13%. Again, that's compared to a 65% maximum efficiency with the Carnot cycle. Sorry about the mistake there. I should have caught it earlier. I just kept going on. So take care, ladies and gentlemen.